Hello everyone, this is 10.2, Calculus with Parametric Curves. So let us recall that for parametric curves we have x as a function of t, y as another function of t, where t is any real number and it's known as what is called the parameter. And in this section we'll be taking a look at basically four different things. I'm not really going to focus on surface areas too much, but I'll just touch on the formula at least. But it's just what we have seen before, so it's not super complicated. But the main ones I really want to focus on are these three. So tangents and concavity, area, and arc length. So let me just discuss real quickly what each of these we'll discuss, and then we'll dive into each one in more detail. But for right now, let me just say tangents and concavity describe the derivative. So this is going to be dy dx and d squared y over dx squared. In other words, the first derivative and second derivative. So if you recall from calculus 1, the first derivative represents the slope of the tangent line. The second derivative represents how fast it's changing. So where the second derivative is positive, it tells you that the graph is concave up. Where it's negative, it's concave down. Similarly, where the first derivative is positive, the graph is increasing. Where it's negative, it's decreasing. Where it's zero, there's horizontal tangent lines. Where it's undefined, there's a vertical tangent line. And for the second derivative, when that's zero, that's where you have possibly an inflection point. But anyways, just something to think about. We'll discuss how to find these things given these parameters. And then area, if you recall, area under a graph of f of x, here I'm using f already, so let's just say it's the integral from a to b of capital F of x dx. That's what area under the curve is, so we have values here. Otherwise, if there aren't any set values, and it may be an infinite area as we've seen before. But we'll discuss this, as well as arc length. Now let's recall the arc length formula for a function of x, let's say f of x, is L is equal to, we have the integral from a to b of the square root of 1 plus the function's derivative squared dx. And there are other ways of describing this as well that we'll get to. And then finally for surface area, we had S was equal to 2 pi integral from a to b of the function multiplied by the square root expression that we have for arc length. So they're super similar. And there are also different variations of this, of course, as well. Move that a little bit outside. Looks better. And like I said, we're going to dive deeper into each one of these. Let's start with tangents and concavity. Right, so the first thing we need to discuss with tangents and concavity is how we find the derivative dy over dx. So if you kind of just figure out what these things are, x is a function of t and y is a function of t. So what you can do is you can actually differentiate each of them with respect to t. So that's kind of what we're going to do here. And what I'm going to do basically is take advantage of this differential Leibniz notation and use basically the chain rule to write this as the following. It is going to be dy over dt multiplied by, now I want to say dt over dx. So the dt's kind of cancel out. The problem is we don't know how to do dt over dx because t is not a function of x. This would imply that t is a function of x and you can take its derivative with respect to x. But it's quite the opposite. X is a function of t. So what we can do instead is write this even better as dy over dt divided by the reciprocal of dt over dx, which is dx over dt. This makes a little more sense. Basically, let me just highlight in red here. This is g prime of t. And this right here is, of course, f prime of t. And that's basically what you do. You find the derivative of y divided by the derivative of x with respect to t, and that actually represents the derivative as, dy over dx. And what about the second derivative now? So this is just a proof for the first derivative. In fact, if you want to box this, we can certainly box this, but to be quite honest, I wouldn't include the middle guy here. This is just a middleman to explain why this is true, using the chain rule and kind of abusive notation. And now finally for the second derivative, which is d squared y over dx. That's just d over dx of dy dx. So taking derivative of the derivative with respect to x once again. And we're going to apply the same thing we did here. If you notice, all we really did is divide top and bottom by dt, which is true by chain rule. So I'm going to do that here in this differential part. Divide by dt, divide by dt. And what we're going to end up getting actually is the following. And it's a little weird to look at first, but with a few examples, it should make a lot of sense. So it's d over dt of dy over dx. Then divide this by dx over dt. Yeah. So this dx over dt part is, well, this guy right here. Where here, this is not really multiplication, this is taking the derivative of that. It's a differential operator. So I know it may seem a little confusing for a little bit, but if you try to replacing dy dx with this expression and multiply top and bottom by each of these, it's an incorrect formulation actually. So long story short, our formulation for the second derivative, dy squared over dx, that should be dx squared, is this. So here, if you cross out the middleman, this is what we'll be using. So basically just take derivative of your derivative you just found with respect to t, and then divide that by dx dt. So now we'll take a look at an example that will involve, well, both of these, and it'll be a pretty involved example. Let's take a look. Right, so for this example, we are asked to find dy dx and d squared y over dx squared, and then they ask for which values of t is the curve concave up. So it seems simple enough. Just find the first derivative using the previous formulation, use that to find the second derivative along with the second formulation we just saw, and then try to see when the second derivative is positive. That will correspond to the curve being concave up. So let's take a look. So dx dt, well, I guess dy over dx really, is dy over dt over dx over dt is what I meant to say. Anyways, so let's do this. So derivative of y with respect to t is 2t plus 1 over derivative of x, that should be dt, with respect to t is just 2t. And if you want, you could split this up. I don't know if it's going to be necessary to do that. It may actually, because we need to take derivative again with respect to t for the second derivative. But for right now, this is part of our answer because we were asked to find that after all. So I'll box this. But let me just say, just to play it safe, if you split this up as 2t plus 1 over 2t, you can write this as 1 plus 1/2 t to the negative 1. So I'm just going to underline this in red because I feel this will come in handy. Just kind of a gut feeling. Okay, now let's see. Second derivative now, d squared y over dx squared. Well, we saw that that is just what? That's d over dt of the derivative we just found, and then divide that by dx dt. So it's almost like doing this to y. It's kind of hard to see this, but let me just actually rewrite that so you can kind of have a better understanding of why this formulation is even true. So this dy over dt, let's imagine instead it's like this, of y. This is of y. So the question is, how do you find the derivative with respect to x of a function y of x? Well, you take d over dx of that. But d over dx is equivalent to doing this, d over dt of that function and then divide by dx dt. So if we want to find the derivative of the derivative dy over dx, notice here, this is in place of our y. This is y prime really. So if we want to find derivative with respect to x of y prime, you take its derivative with respect to t and then divide by dx dt. Because that's exactly what we did for y to find y prime. So I don't know if that cleared things up more or not, but that I think is a better explanation of the previous formulation we saw. But in any event, let's continue. So we want to find the derivative of dy dx with respect to dt again, with respect to t again. So it's good that I wrote it like this, otherwise you'd have to use a quotient rule here, and I don't want to do that. So I'm going to find derivative of this that I underlined in red, and its derivative with respect to t, that's what d over dt means, is 0, so I'm not going to write it. And then the negative 1 comes down, so it's negative 1/2 t to the negative 2, because by the power rule you subtract 1 from the power again. Over dx dt, and we already found dx dt, that's derivative of this with respect to t, which is 2t. So yeah, there's definitely a way we can simplify this, of course. We can write this as, well, let's see. This is negative 1/4 t to the negative 3. So maybe if you want, we could write it like negative 1 over 4 t cubed. I hope we're okay with that. So I'm not really explaining my work here. You can kind of check it out. If you wrote this as that over 1, and you wrote this t to the negative 2 as 1 over t, and multiply this whole numerator by the reciprocal of this denominator, you'll see you'll have 2 2's in the bottom, which is 4, 1 t in the bottom, well I guess 2 t's in the bottom because it should be t squared, there we go, and 1 other t in the bottom after reciprocating, so in total you have 3 t's in the bottom. And there we go. And now the question is, when was this concave up? Well, when this is concave up, so I have some space to write this on the bottom. So the curve is concave up when the second derivative, dy, well, d squared y over dx squared, is positive. So that means negative 1 over 4t cubed is positive. When does this happen? Well, without solving this too much, I mean, you can reciprocate both sides and get rid of the negative, and the inequality symbol will flip a few times. But I think, long story short, we kind of agree. This appears to be at face value a negative value because of the negative sign. T cubed is an odd operator, meaning that, it's an odd operation, meaning that when you apply it to a negative number, the negative comes out. So to make this negative go away, we'd have to have t be negative, because then a negative number cubed is still negative, and then double negative is positive. So this only happens when t is negative. And notice t can't be 0, because when t is 0, you'd have a 0 denominator here, and the second derivative wouldn't exist. So when is the curve concave up? It's concave up when t is less than 0. And specifically, they said for which values. So if you want to write this in interval notation, I guess you can say negative infinity to 0 as an interval notation way of writing it. But, whatever works. And that was it for this example, and I kind of want to do one more that will get a little crazier. So let's do one more on this topic. Alright, so let's read this example. It says, find an equation of the tangent to the curve at the given point by doing each of these. First, not eliminating the parameter first, and then secondly, eliminating the parameter first. So at first it may seem like it's a lot that's being asked of us, but in reality the procedure should be kind of clear. It's basically saying find the derivative, which is the slope of the tangent line, evaluated at this point. Now it says point. What does that imply? That implies that this is an x value and this is a y value. So keep that in mind. Now the derivative is the slope of the tangent line, and remember that is just dy over dx. And we know dy over dx is just dy over dt over dx over dt. So for a, that's what we're using. So let's roll with that. Let's see what happens. So derivative of y is just 2t because 2 goes to 0. Okay, what about dx dt? Okay, let's see. Derivative of 1 is 0, so that goes away. Derivative ln of t is 1 over t. So we could bring it up to the numerator and end up getting 2 squared, or 2t squared. Great. Now what? Well, now we need to evaluate it at this point here, and it's kind of difficult to do that if you don't know what the t value is. So I guess the first thing we need to do is figure out what t value will give us these values. So let's kind of think for a second. When is this equal to 1? So it's a question mark here. And when is this equal to 3? Well, I mean, that's actually a pretty simple question, because look, in order for this to be 1, that has to be 0. And we know ln of 1 is 0. So t equals 1 seems to work for x, because you get 1 as your x value. And if this is 1, 1 squared plus 2 is also 3. So it seems like in order for this to work, this has to be at t equals 1. So then evaluating this derivative at this point would be the slope of the tangent line at this point of tangent t. We would just merely have to evaluate this expression in t at t equals 1. So the derivative, well, I guess the slope of the tangent line really at this point is just 2 then. All right, now what? Well, now using point slope, we could say that the equation of the tangent line is y minus the y value times the slope times x minus the x value. Then you can solve for y if you want to write it in slope-intercept form. So if you distribute this, you get 2x minus 2, and then if you add 3 to the other side right here, like this, you end up with y is equal to 2x plus 5, and that is our answer. That's the same answer we're going to get for part B. Now notice, the only real difference is finding this glorious 2 here. So how we found it here was we first had to find the derivative using our formulation involving parameters, but then we also had to figure out what to evaluate it at, and that was a little tricky. Now for B, what's going to be the tricky part is going to be, let me separate this first, is going to be limiting the parameter. Once that's done, then we find the derivative and evaluate it at this point. So let's see how that goes. Now I gave you the idea in the last section that to eliminate a parameter, you can solve for t in one variable and then substitute that into the other. And here if you solve for t, you get a square root because you have to subtract and then square root. And it gets funny because you have to take get a plus or minus when you take square roots. Here, the inverse of ln of t is e to the t. There's no catches with domains, so you don't have to worry about plus or minus. So this, I think, is better to solve for t. So if we have x equals 1 plus ln of t, and we subtract 1, we get x minus 1 is equal to ln of t. And then if we take both sides as powers of e, we get e to the x minus 1 is equal to t. So let me write that here. So we end up getting that t is equal to e to the x minus 1. Perfect. So now if we plug that into the y equation, we then get what? We get y is equal to that squared, so e to the x minus 1 squared, meaning you just multiply the power by 2 and then plus 2. So this is e to the 2x minus 2, distributing this 2 into the power here, and then plus 2. So this is y. Now what do we want to find? We want to find dy dx. So now let's see if I not cut off here. I think that's good. Good. Dy dx is just, well, y prime. Derivative of this is itself because it's e, but then by chain rule you have to multiply by the derivative of the power, which is 2. So it's 2 e to the 2x minus 2, and that plus 2 goes to 0 because it's a constant term. And then what do we evaluate this at? We have to evaluate this at the x value of the point, which is 1. And when you plug in 1 for x here, what do you get? You get 2 times e to the, well, in the power here, when you plug in x to be 1, you end up getting 2 minus 2, which is 0. E to the 0 is just 1. So we indeed get this 2. And then this point slope form part was just the same for both A and B. Whew, nice. So it's kind of complicated, but there we go. We actually made it through. And it wasn't too bad of an application of finding tangents and I guess finding second derivatives for the previous example. But anyways, that's kind of all I wanted to say on that end. Now let's talk about areas, and then we'll go on to arc length and then finally surface area. All right, so for area, we want to find the area under the curve of some curve f of x. So remember, it's y equals f of x. So y is a function of x here. And it's between these x values, a and b. So this is x equals a and x equals b. Now, if y is g of x, g of t, function of t, g of t, and x is a function f of t, let's use lowercase f because we're using capital F here, then the following is true. So notice this is the integral from some x values a to b of y dx. Okay? What if you found the derivative of x, because we want dx, of course. So this what this reminds us of really, I think, is substitution, use substitution. only it's like t substitution kind of. So dx then would be f prime of t dt. Y is a function g of t. Dx is replaced with f prime of t times dt. And what about these x values? Well, these x values have to change into t values now. Now, how that's done, that can be kind of tricky. Basically, you want to plug them in to x to see what t would be. So you want to solve for t for each of these. So you kind of have to do that sort of maneuver there. And we'll see that in this example. And this will be the only example we'll be taking a look at for areas. But let's see. So it says find the area under one arc of the cycloid. X equals r times the quantity theta minus sine theta, and y is equal to r times the quantity 1 minus cosine theta. Now, if you're not familiar with the term cycloid, it's basically a shape that will kind of continue periodically, but it actually is only above the x-axis, not below. So it's not really like a sine wave. It's a little different, but it still has a period. Now the period will be 2 pi r. So it goes from 0 to 2 pi r, so the length of this interval is 2 pi r, where r kind of varies. So r isn't really a variable here, r is a constant because it depends what r is equal to. That'll tell us what this x value would be. So we're going to treat r as constant here. So here in reality, the parameter variable is theta. Not t, but theta now. So, well, we want to see if we can find the following. We want to find the integral from 0 to 2 pi r of y dx. That's what this area represents. Area under the curve is, well, we're treating this as a function of y of x. Y is a function of x. And instead of separating or eliminating the parameter, which maybe you can do, but it seems a little challenging here, we're just going to apply this formulation here, which is really this guy. So maybe you should box this, I guess, if you like. So we have to change the limits, so I'll do that in due time. But the y dx, y is just this, r times 1 minus cosine of theta. And dx, remember, is f prime of t dt. So it's going to be the derivative of this with respect to theta and then d theta. Now notice, r is just a constant here, so r will stay the same. Derivative of theta minus sine, derivative of theta is just 1 with respect to the variable theta. Derivative of sine is cosine, sine stays the same. And then we get our d theta. Yikes. Yeah, this doesn't seem super pleasant. Because of course the r squared can be pulled out, and that's fine. But now after foiling out everything else, 1 minus cosine times 1 minus cosine is 1 minus 2 cosine plus cosine squared. And this, I don't think, is really nice of a situation to be in. And the reason there being is because the antiderivative of cosine squared requires that power reducing formula we saw way long ago in chapter 7. So we're going to have to apply that here. Let me at least get our limits situated though. So when is x 0? What value of theta would give you an x value of 0? Well, r is constant, so this would have to be 0. Notice, if this is 0 and, well, theta is 0, so if theta is 0, we'll have 0 minus sine of 0. So that's 0. So the theta value there that works is actually theta equals 0. So the bottom limit is still 0. Okay. What about 2 pi r? Well, in order for it to be 2 pi r, this r is kind of safe in some sense. And this would have to amount to 2 pi. Now the nice thing here is when theta is 2 pi, this will be 2 pi minus sine of 2 pi is 0. So it'll be r times 2 pi, which is indeed 2 pi r. So this, I think, will have to have a theta value of 2 pi to make that 2 pi r. Perfect. So now we know what we're trying to do here. Let's continue by me erasing this for more space. I'm going to erase this, shift this up, and we'll continue. Right, so here we are, and I wanted to include what our power reducing formulas we found, well, before. And of course I included both, but we really only need the top one. Also, I kept the image here because I thought it was kind of cool looking. But yeah, let's continue by first doing this. So antiderivative of 1 with respect to theta is just theta. Antiderivative of cosine is positive sine. So this will be -2 times sine of theta. Okay, so far so good. Now, for the antiderivative of cosine squared, we first need to write this as being equal to, let's distribute this, might as well. So we get 1/2 plus 1/2 cosine of 2 theta. And now we'll antiderive this. So the antiderivative of 1/2 is 1/2 theta. The antiderivative of cosine is, well, sine, positive sine. And, so let me just say this. Since it's of 2 theta, we have to divide by an additional 2. Since we already have 1/2 here, we're multiplying by 1/2 again. So that'll leave us with 1/4 now. And we're evaluating this finally between our limits, 0 and 2 pi, and we're multiplying by r squared after the fact. So let's get on to it. Notice also that these combine to 3/2 theta. So this is going to be 3/2, plugging in the top one, so it's 2 pi, minus 2 sine of 2 pi, plus 1/4 sine of 4 pi. This is the first valuation. The second is plugging in 0. Sine of 0 is 0. So for these two, these will both be 0. And when you plug 0 into theta, you'll also get 0 actually. So we don't even need to do that one. It'll just be -0. And this is, of course, multiplied by r squared. And again, sine of 2 pi is 0. Sine of 4 pi is also 0. So all we're left with, well, these cancel. So we're left with 3 pi r squared actually as our final answer. Whew, nice, how fun. So now we're going to move on and talk about arc length and then finally surface area. All right, so now for arc length, like I was saying earlier, here f of x is our y. So f prime of x would be dy over dx. And what I want to do here is I want to obviously get t into the mix. So again, it may not be obvious, but a lot of the things we've been doing here kind of make sense for what I'm about to do. I'm going to write dx as dx over dt times dt. And I want to bring it into the radical. I want to bring the dx part into the radical. So what I'm going to do is this. So there's going to be a lot of manipulation here. But this dt, I'll leave outside of the radical. And we're replacing this dx with this whole thing. So this dx is gone. Dx dt, I'm bringing in as a square. So dx dt squared into this radical. And inside the radical, what do we have? We have 1 plus dy over dx all squared. Okay, this is actually good. There's a lot of good news here. If you distribute this dx over dt squared into this, well, a few things happen. First off, the first part here inside the radical becomes 1 times that dx over dt squared. That's fine. Plus, what happens when you multiply it into this? They're both squared, so it's going to be the whole thing squared. The dx's will cancel, so we have dy over dt only. So I'm leaving out a little bit of details, but that's basically what you get. And that dt is on the outside of the radical. And of course, since these are x values technically, a and b, they're now changed to t values, which we'll call alpha and beta. And I believe that's what I called them in the previous discussion on areas. Something I didn't mention, by the way, is a kind of technicality detail that you need to kind of consider sometimes for areas. The direction depends, because remember for parameters, for parametric curves that is, there's a direction that I haven't really been mentioning in this section too much. And it's not too big of a deal, to be quite honest, but it kind of makes a difference sometimes where your alpha and betas are located. Now for arc length, we're assuming that it's in this order and the alpha is smaller. So here the direction is such that alpha is less than or equal to beta. So our t value is going to be in between alpha and beta, of course. And it needs to be in the positive direction. Another thing too is we're assuming that this curve is only traversed once. because if it was twice, then you get like a double arc length. It gets a little fishy. So we're only going to be handling simple scenarios. In fact, I'm only going to do one example, like I've been saying. So let's see. So here, again, I'm stuck in the same kind of idea that we saw for areas with the cycloid. So I want to find the length of one arc of the cycloid. So here it is. Now, instead of shading the area in red, I shaded, well, I guess not shaded, but I traced the arc length we want in red. And something we found out here is that this happens from this point to this point. Here, theta is 0, and here, theta is 2 pi. We actually figured this out from the previous example. So our limits are going to be from 0 to 2 pi. So our arc length formula will be, so just to kind of finish this thought off, this was the main conclusion of arc lengths with parametric curves. So now, finally, for this example, our arc length will be the integral from our t bounds, 0 to 2 pi, of the square root of what? Well, we have dx over dt squared, so let's find the derivative of this. Now again, there's no t here, it's theta instead of t, so there shouldn't be d theta on the outside. Let's see, derivative of this is 1, derivative of sine is cosine, r stays, so it's going to be r times 1 minus cosine theta, and then that's all squared, so we actually get r squared and this squared, because we're squaring that quantity after we take its derivative. That's what this means, dx over dt all squared. And also need a little bit more space for the next term. Let me make space. So plus what? Doing the same thing here, let's see what happens. So derivative of a constant times this is just, again, r times that. So r stays. Derivative of 1 minus cosine, well, derivative of 1 is 0, so don't write it. Derivative of negative cosine is positive sign, because derivative of cosine is negative sign. And then we have to square each of them, because we're squaring the whole thing. So we'll get r squared sine squared. Weird. We have a little bit of space, so I'm going to try to simplify this a little bit here. Let's see. So r squared is what they both have in common. In fact, you can pull that out of the radical and out of the integral by square rooting r squared. So outside of this integral, we have just r now. And if you actually expand 1 minus cosine all squared, that's 1 minus 2 cosine plus cosine squared, and then we have plus sine squared, and then d theta. Now remember, cosine squared plus sine squared is 1, and 1 plus 1 here is just 2. We can possibly pull that 2 out, so hopefully I have space, but we'll have r times the integral from 0 to 2 pi of the square root of, I would write 2 minus 2 cosine, but if you pull the 2 out, you get 2 times the quantity 1 minus cosine of theta, d theta. Now at this point, it kind of seems like we're at a little bit of a loss. It's really hard to go from here. But I'm going to show you some trickery with the double angle formula. In fact, with the power reducing formula we saw earlier, I'm going to use the one for sine because this is 1 minus cosine. So we'll take a look at that right now. Right, so this is what we just ended up with. And as mentioned, here are the power reducing formulas that we spoke about in the previous example. And I want to focus in on sine squared because it's 1 minus cosine. So I want to do my best to rewrite this in terms of this. So let's kind of think, well, just try to follow me here. So if we replace 2 theta with theta, so 2 theta is our new theta, then theta would be half of theta, so that's theta over 2. I know it sounds weird because I'm using theta here, and I want to use theta because that's our variable. So you know what, let's do this. Let's imagine this wasn't theta. Let's imagine it was, I don't want to say u, let's use phi or something like that. So if 2 phi is equal to theta, then half of 2 phi is phi, which is theta over 2, it's half of theta. So this part I think should make sense. So what I'm trying to do is I'm trying to convince you of something, and I want to basically manipulate this so that it looks like this, and we're so close because we have 1 minus cosine of theta and there's 1 minus cosine of theta. All we need now is this 2 outside of parentheses, not a 1/2. And if you multiply both sides by 4, What's 4 times 1/2? It's 2. So you end up with actually is that this trig identity turns into this one. 4 sine squared of theta over 2 is equal to 2 times 1 minus cosine of theta. It got cut off a little bit, but that's 1 minus cosine of theta. And that's just this inside the radical, which is great because now it's squared and we can square root that. So this is our integral from 0 to 2 pi of the square root of that, which is now just this quantity here. So it's 4 sine squared of theta over 2 d theta. Great. Now we can square root. The square root of 4 is 2. The square root of sine squared cancels the square. And now this is, well, we can pull the 2 out. So it's 2r integral from 0 to 2 pi of sine of theta over 2. Whew, nice. Now theta over 2, of course, is 1/2 theta. I like writing like that better. It's easier for me to see because the multiple of theta. Antiderivative of sine is negative cosine. Since it's of 1/2 theta, what do you have to do? You have to divide by the derivative of the inside because the inside is linear. Derivative of the inside is 1/2. Dividing by 1/2 is multiplying by 2, so it's negative 2. And then we evaluate this between 0 and 2 pi. Now remember, any constant multiples you can do after or before the evaluation. It doesn't matter because of distribution. So this negative 2 I'm going to pull outside with this 2r to make negative 4r. So it's negative 4r and then this. Now of course if you wanted to get rid of this negative you can flip this, but we'll see it all come together in the end, I think. So let's see. So we'll have negative 4r all multiplied by, let's do it now. So when you plug 2 pi in here, you get cosine of 1/2 of 2 pi, which is just cosine of pi, minus cosine of 1/2 times 0 is cosine of 0. Whew, great. So cosine of 1/2, or cosine of pi is negative 1. Cosine of 0 is 1. So what's that? That is negative 2. Negative 1 minus 1 is negative 2. So that is negative 4r multiplied by negative 2. And there we go. We get positive 8r, which is our answer. Now I'm going to talk real quickly about surface areas. I'm not going to do an example because I don't want to focus on it too much. I just want to kind of show you what things are. But you'll see it's really what we saw earlier in that section. But maybe it'll give you more light on what was happening in that section on surface area. So let's take a look. All right, so for surface area, like I was mentioning earlier, the formulations we saw in 8.3 are actually still valid. There's really no difference. And I'm going to try to explain why a little bit. So remember that this is y. So we know y is a function of t, so that's fine. Also, we actually know, based on our formulation for arc length with parametric curves, this, if you let f prime be dy over dx, and you replace dx with dx over dt times dt, bring that in as a square inside the radical, this will actually all turn into the following. The square root of dx over dt all squared plus dy over dt all squared. And then the dt outside of the square root. Okay, great. And this is just y. So y is going to be a function of t. And this, what you can actually do is you can call this ds. So the shorthand for this formula is surface area is 2 pi times the integral from t equals alpha to t equals beta of y times ds, where alpha is less than t is less than or equal to beta. And now this is for rotating the curve of y as a function of x about the x-axis. So there we go. Now, what about if you wanted to rotate about the y-axis? Well, about the y-axis, you just replace all y's with x's and vice versa. So here you'll get the surface area is 2 pi times the integral from maybe not the same t, well, I guess it will be the same t values because it's the same curve length, the same section of that curve, and then rotating about the y-axis now. So this will be x ds, alpha is still less than t is still less than beta, and this will now be about the y-axis instead of the x-axis. So it's a little more simpler looking, but in fact it's really the same formulation from 8.3, and hopefully this kind of explains things better as far as when you were to use one of whichever one of the two, because the way we went about that was we had a function of x and sometimes we had a function of y, and there were two different formulas. But here what I'm saying is if you just use a shorthand formula, then you can just stick with these two versions instead. Of course, sometimes you're in a weird situation where you have to use one of the four that we laid out in 8.3. But again, for that reason, that it's kind of the same, I don't want to do any examples on this. I just wanted to show off these really nice formulations of the surface area, but for parametric curves. It's the same thing, only, well, y and x are functions of t, and ds is basically the radical part of the arc length formula. Great, so that concludes 10.2. It was a lot of fun. See you in the next video for 10.3. It's going to be very interesting. See you then.